All right, so in this section, Lecture 5, Part 3, we talk about the fundamental theorem of calculus. And it's a particularly important result because it will relate the evaluation of integrals to antiderivatives. The fundamental theorem of calculus establishes a connection between the two branches of calculus, namely differential calculus and integral calculus. Differential calculus arose from the tangent problem. Integral calculus arose from a seemingly unrelated problem, the area problem. So we're going to relate the two. So differentiation and integration happen to be inverse processes. So the fundamental theorem of calculus, called FTC, gives the inverse relationship between the derivative and the integral. And what it does is it allows us to compute areas and integrals without having to compute them as limits of sums, as we did in the first two sections of this chapter. So the first part of the FTC deals with functions defined by an equation of the form g of x is equal to the definite integral from a to x of f of t dt, where f is continuous on a to b and x varies between a and b. So this is a functional notation. Both functions, the function on the left and the function on the right, are functions of x. Okay. So g depends only on x, which appears as the variable upper limit in the integral. If x is a fixed number, then the integral is a definite number. If we let x vary, the integral from a to x f of t dt also varies and defines the function x denoted by g of x. All right, so bear this in mind. So if f happens to be a positive function, then g of x can be interpreted as the area under the graph of f from a to x, where x varies from a to b. So you can see the dichotomy here. Red curve is f, or f of t, so we have the t-axis, okay? Then we select an interval on the t-axis from a to b, and then x is some number between a and b, and then we designate the area g of x as the area under f of t from a to x, where x is less than or equal to b. So we can think of g as an area so far function as seen here. All right, so understand this geometric relationship. So for example, if f is the function whose graph is shown and g of x is the area under the curve from 0 to x, find the values of g of 0, g1, g2, g3, g4, and g5. And then it asks to sketch a rough graph of g. All right, so g of 0 looks like it will be 0. G of 1 evidently will be the area of this triangular region. G of 2 will be the area of this triangular region plus this square region right here. Okay, so the square plus the triangle is g of 2. G of 3 will be the area under the curve from 0 to 3. G of 4 will be the area under the curve from 0 to 4, and so forth. All right, so let's see how they approach this. Okay. So g of 0 is the area under the curve from 0 to 0 of f of t dt, and we note from the properties of integrals, when the upper and lower bounds of the definite integral are the same, then the definite integral evaluates to 0, and that's verified by the drawing. Now, g of 1 would be the area under the curve from 0 to 1, and that's just the area of the triangle, which is 1/2 the base times the height. And so that is obviously 1. So far, so good. G of 2, you'll have to add the area of the rectangle. So g of 2 is the area under the curve from 0 to 2 of f of t dt, okay, which we can split into a sum of two integrals using the properties of the integrals, from 0 to 1 and from 1 to 2, and so that would be the area of the triangle plus the area of the rectangle, which is 3. And notice how we split. The split comes from knowledge of properties of the integrals. We can split the integral into a sum of two integrals. All right, so going forth, g of 3, I guess, right? So g of 3 is g of 2 plus the definite integral from 2 to 3 of f of t dt. And so they provide an approximation. So let's guess that the area under the curve from 2 to 3 is approximately 1.3 square units. So that would be an estimate. We'll go with that. Although there's no concise way of knowing it's 1.3, we'll just estimate it as 1.3. So the area from 0 to 3, the area under the curve from 0 to 3 is 4.3. Right, now for t greater than 3, of course, f of t is below the x-axis. And so we start subtracting areas as follows. All right, so g of 4 then would be g of 3 plus the definite integral from 3 to 4 of f of t dt. And so once again, they estimate the area of this blue negative zone to be minus 1.3, the symmetric counterpart of the portion of the graph from 2 to 3. And so we're back to 3. So g of 4 is 3. And then g of 5 would be g of 4 plus the definite integral from 4 to 5 of f of t dt. And so again, by symmetry, I guess we're playing a symmetry game here. The area from 4 to 3 would be negative 1.3. And so thus g of 5 is 1.7. And we'll take that to be the area under the curve from 0 to 5. Okay, so they use these values to sketch the graph of g. So g of 0 was 0. Notice that because f of t is positive for t less than 3, we keep adding area for t less than 3. Okay, so for g, so g is increasing up to x equals 3, where it attains a maximal value. And for x greater than 3, g decreases because f of t is negative. All right, so so what were the points? G of 5 is 1.7. So 1.7. So, and another thing that's not mentioned in this slide is the fact that they connected a smooth curve through the points that they plotted. So G of 4 was 3. G of 4 was 3. Okay, so G of 3, I guess, was 5. What was G of 3? G of 3 was 4.3. So here's 3, 4.3. We know 0 was on the graph, and so forth. And so what they did was they connected the points to form a smooth curve like this. All right, so this would be g as a function of x. So here's your graph of g of x. All right. Okay, so far so good. So if we take f of t equal to t and a equal to 0, okay. Okay, so, well, did I skip a slide? I just made an abrupt transition in technical content here. Okay, well, anyway, so we want to evaluate this particular definite integral right here. So f of t is equal to t, and we want to evaluate its integral, say, from so here's x. Okay, and so we're trying to find g of x is evidently equal to the integral from 0 to x of t dt. So basically, g of 0, of course, would be 0. G of 1 would be the area under the curve from 0 to 1, which would be 1/2 the base length, which is 1, times the height, which is 1. So g of 1 is 1/2. Okay, g of 2 would be, okay, so if this were 2, that would be 1/2 the base times the base length times the height, which is 2, so that would be 2. So g of 2 is 2. All right. G of 3 would be what? So instead of 2, supposing this were 3, so g of 3 would be 1/2 times 3 squared, and so forth. So I think you get the picture. So no matter what x you choose, the area under the curve will be 1/2, the base length will always be x, and the height will always be x. And so that's 1/2 x squared, right? So the g of x for this, which denotes the area under the curve from 0 to x, is x squared over 2, right? Just using the area of subsequent areas of triangles. Okay, so we just did exercise 27 of section 5.2. So the derivative of g is x. That is, if we take the derivative of g, that would be, using the power rule for differentiation, that would be x, which also happens to equal to, well, if we consider this function t, if that's f of t, so if f of t is equal to t, then f of x, of course, is equal to x. Okay, and so g prime of x happens to equal to f of x, which equals to x. Right, so notice that relationship for this particular function. G prime of x is equal to f of x. If g is defined as the integral of f by equation 1, g turns out to be the antiderivative of f in this case. So in this case, g is the antiderivative of f. So if f is x, recall what the antiderivative of x is. The antiderivative of x, we have said, is x squared over 2 plus c, and we can take c to be 0 for a case where c is equal to 0. Right? For this function. May not be the case for other functions. If we sketch the derivative of the function g, as in the first figure, by estimating slopes of tangents, we get a graph like that of f in the second figure. So remember, in the first example, we calculated g for different values of x. And so from 0 to 1, we see that the function, if we estimate the slopes of the tangents to g from 0 to 1, we see that it's kind of increasing. And then from 1 to, say, 2, it's kind of a linear, a straight line relationship. Okay, and so we know that the slope of a tangent line to a line is just the slope itself. And so we can estimate the slope from 1 to 2. Okay, so from 1 to 2, what is the slope of this line? Well, delta y over delta x, right? So that would be 3 minus 1, which is 2. 2 over 1 is 2, and so you can see from 1 to 2, the slope is 2. And then from 2 to 3, okay, we know at 3, it equals 3, the slope of the tangent line is 0, so we'll have a 0 there, of course. And then we can kind of estimate that the slopes of the tangents range from 2 down to 0, 2 down to 0. And then from 3 to 4, we see that the function is a decreasing function. So at 4, the slopes of the tangents stop decreasing and they start increasing slightly. Okay, and then finally at 5, at t equals 5, we have no more information, and so we'll go ahead and say that the slope of the tangent at t equals 5 is 0. Okay, so notice that if we were to if we take the graph of g and plot the derivative of g, we would get back our original f of t. So in this function, we can make the claim that the antiderivative of f is g, okay, or g prime is equal to f from the sketch. And that's just an approximation reading from the graph. We haven't proven that yet. That's what the FTC will do. All right, so to see why this might be generally true, we consider a continuous function f with f of x greater than or equal to 0. All right, so the orange curve is f, hypothetical f on the t-axis from a to b. All right, so g of x is the area from a to x of f of t dt. So g of x will be the area under the curve this area right here. All right, so the area under the curve, like right here. All right, so there's your g of x. And then in the next slide, I suspect we're going to calculate g of x plus h. All right, so maybe I should. So I'll move this off to the side. So to compute g prime of x from the definition of the derivative, we have first observed that for h greater than 0, g of x plus h minus g of x is obtained by subtracting the areas. Okay, so you realize, of course, that this blue area is g of x plus h, the area under the curve from a to x plus h. All right? So this blue area is g of x plus h, and then the green area is g of x. So when you subtract the green area from the blue area, you'll end up with this orange strip from x to x plus h. And that area, that orange strip area, is g of x plus h minus g of x. It's the area under the graph of f from x to x plus h, the gold area, that is, they call it. I call it the orange area. I can't tell. All right? So what next? Okay, so g of x plus h minus g of x is approximately equal to the width of the rectangle times the height of the rectangle. So I guess we could take the height of the rectangle to be at the left endpoint of the strip. So g of x plus h minus g of x is approximately equal to h times f of x for small h, okay, for small h. And so if we divide both sides by h, we'll have g of x plus h minus g of x over h is equal to f of x. So in other words, the difference quotient of g is approximately equal to f of x. All right? So if we take the limit as h approaches 0 of the difference quotient of g, we have the derivative of g by definition. And this, of course, now if we take the limit as h approaches 0 of f of x, well, that's just f of x because f is not a function of h. So the derivative of g is equal to the function f. Okay, and this fact is true even when f is not necessarily positive. And this is the fundamental theorem of calculus part 1. Okay, it was proven from this figure. If f is continuous on a to b, then the function g is defined by g of x is equal to the definite integral from a to x of f of t dt, where x is between a and b, okay, on the interval. G of x is continuous on a to b and differentiable on the open interval a to b, and g prime of x is equal to f of x. So the derivative of g is equal to f. Okay, so there we have a relationship, but the differentiation is the undoing of integration. So if we differentiate both sides, we peel back the integral and expose the function, and we're left with the derivative on the right-hand side. All right. The FTC says that the derivative of a definite integral with respect to its upper limit is the integrand evaluated at the upper limit. All right. If x and x plus h are both in the open interval a to b, then g of x plus h minus g of x, okay, would be, again, here's the reference figure. Okay, so g of x plus h is the area under the curve from a to x plus h of f of t dt minus the area under the curve from a to x of f of t dt. It's this golden strip, right? And so what we do is we know that the integral from a to x plus h can be replaced, expanded into two integrals by splitting the integral. So we're going to split the integral this way, okay? So we're going to go from a to x, and then x to x plus h, okay? And then we subtract off the component from a to x, okay? So we're left with this piece right here. Okay, so g of x plus h minus g of x is equal to the width of the strip x to x plus h times the height of the strip, which is f of t. Okay? All right, so this is the fundamental theorem of calculus part 1. So here we have the difference quotient equal to 1 over h times the area under the curve. Basically, we divided both sides of the equation by h. Okay, and then of course we'll take the limits. So since f is continuous on x to x plus h, the extreme value theorem says that there are numbers u and v in the interval. X to x plus h says that f of u is equal to the smaller value and f of v is equal to the larger value by the extreme value theorem. So m, lowercase m and uppercase m are the absolute minimum and maximal values of f on x plus h. All right. So we're going to assume that h is greater than 0. All right, so we'll keep this figure in mind. So we see from x to x plus h, somewhere between x and x plus h, there's a value u such that the function y equals f of x attains a smaller value, and at v, f of v, where v is between x and x plus h, the function attains a larger value. And this is done by the extreme value theorem. Okay, so, and we're going to assume that h is greater than 0. Okay, so this is essentially the proof of the mean value theorem. I mean, not the mean value, the fundamental theorem of calculus. All right. And so by property 8 of the integrals, we know that the true output value of the integral from x to x plus h is going to be wedged between m times the width of the interval and uppercase m times the width of the interval. Okay, so this is kind of the squeeze theorem for integrals. Okay, so m, of course, is, we replace m by its definition in f. It's f of u. And big M is f of v. So we do those substitutions. Okay, so we've got the squeeze theorem evolving. And since h is greater than 0, we can divide this inequality by h. And so we have 1 over h times the integral from x to x plus h of f of t dt is wedged between f of u and f of v. All right, so we have this mathematical relationship. Now it's a math relationship. All right, and so we can replace this expression right here. We know that this is simply g of x plus h minus g of x. Okay, we know that from previous development. So now we have this relationship, and inequality 3 can be proved in a similar manner. What is inequality? I don't know what inequality 3 is. Anyway, we've got this relationship. Okay, so if we let h approach 0, now look at this figure right here. So h, if h approaches 0, if we drive h to 0, then x plus h will approach x. And when the implication is that as we squeeze h to 0, we push u and v on top of x as well. All right, so you can see that as we play the squeeze game. Push x plus h toward x, and then v and u will be pushed toward x correspondingly. Okay, so the limit as h approaches 0 of f of u is equal to the limit as u approaches x of f of u, which, and since by continuity this is a continuous function, we can use direct substitutions. That's f of x. The same case holds for the limit as h approaches 0 of f of v will equal to f of x. All right, and that comes from the limit laws. And so, therefore, we conclude that the limit as h approaches 0 of the difference quotient of g, which is the derivative of g, is equal to f of x. If x equal a or b, then equation 4 can be interpreted as a one-sided limit. Okay, of course. Okay, all right. So the derivative with respect to x, of the definite integral from a to x f of t dt is equal to f of x when f is continuous. Okay, equation 5 says, well, this equation says that if we first integrate f and then differentiate the result, we get back our original function. So differentiation is the undoing of integration. All right, so find the derivative of this function, right? So since f of t is continuous, right, the function is continuous, fundamental theorem of calculus would assert that you take this upper bound argument x, plug it into g, so g of x is equal to f of t evaluated at t equals to x. So you just take the argument of the integrand, plug in x, and you get the derivative of the function. Okay, all right. And there'll be a lot of web assigned questions regarding that. So let's do some more examples. Okay, so we can do the Fresnel function, which is defined like this. Okay. So what do we want? We want to calculate the derivative of the Fresnel function. So again, you just take the integrand, which is sine pi t squared over 2, and plug in x for t, and then you'll have the derivative of the function. Okay. So we see f of x graphed, and the Fresnel function. Yeah, so a computer was used to graph s by computing the value of this integral for many values of x. All right, so there's the integral. S at different values of x, okay. Which we, okay. All right. So that's all right. No big deal here. Okay, so we have visual confirmation. All right, so that's a bit complicated. All right, so now here's where we have to be careful when using the fundamental theorem calculus. It asserts that the upper bound of this definite integral must be x, linear in x. And so in this particular example, the upper bound is not linear in x. So we have to use the chain rule here. And don't be concerned about the lower bound. Don't be overly concerned about the lower bound of the definite integral. So what we have to do is we have to reformulate the upper bound of the definite integral in terms of a variable that's linear. So if we let u equal x to the fourth, the problem would become the derivative with respect to x from 1 to u of secant t of dt. So recall that the derivative with respect to x of something is equal to the derivative with respect to u of that thing times the derivative of u with respect to x. So this is essentially the chain rule, okay? And so what we do then is we'll replace this differentiation in x right here, this piece, with the derivative with respect to u, okay, of the definite integral now formulated in terms of u times, of course, the derivative of u with respect to x. So this is the chain rule. So you have to apply the chain rule to the fundamental theorem of calculus. And so that allows us then to evaluate this integral, which is, of course, merely the secant of u times du over dx. And so u is equal to x to the fourth. So du over dx would be 4x cubed. Okay, and then finally we replace u with its definition in x. So we have secant x to the fourth times 4x cubed. And notice, because of the contrivance of this problem, we never had to alter the lower bound of the integral. Although if we had 2 here, we would probably have to replace it with like another quantity. But the book doesn't seem overly concerned with that. So no need to worry about the lower bound. Okay, so now we go into the fundamental theorem of calculus part 2. All right, so if f is continuous on an closed interval a to b, then the definite integral from a to b of a function f, lowercase f, is equal to the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. So f is any antiderivative of f. Any antiderivative. You remember that integration constant doesn't matter because it will subtract out. Okay, so the derivative of uppercase f, of course, is f. So if we let g of x equal to this, we know from the fundamental theorem of calculus part 1 that g prime of x is equal to f of x, where g is an antiderivative of f. If uppercase f is any other antiderivative of f on the closed interval a to b, we know the corollary from 4.2, that is from the corollary to the mean value theorem, that f and g both differ by a constant. Okay, and so, however, both f and g are continuous, and thus by taking limits of both sides of equation 6, okay, yeah, so it holds. So don't worry about that too much. Okay, so g of a, of course, is from, if we let x equal a, lower bound is a, then that's a rehash, so nothing new there. And so they're just showing you that the integration constants will cancel out in the evaluation of the antiderivative for the definite integral. Okay, so that's just theoretic. Okay. Right, so I guess we have some examples now. So if vt is the velocity, if vt is the velocity of an object and st is its position at time t, then the velocity, of course, is the derivative of the position function. So the position function is the antiderivative of the velocity function. So we considered an object that moves in the positive direction, then we guessed the area under the, yeah, so we did that. And so in symbols, the derivative of the velocity function from a to b, from time equals a to time equals b, is equal to the position at b minus the position at a. And so that's the second fundamental theorem of calculus part 2. So now we can go back and evaluate this integral. So according to the FTC2, we just take the antiderivative of e to the x and evaluate it at 3, and then subtract off the antiderivative evaluated at 1. So the answer is e to the cube minus e. So there's your area under the curve from 1 to 3. Okay. Yeah, so here, notice that in the evaluation of this expression, that the integration constant, that constant, that plus c value, basically what they're saying is this. The antiderivative is e to the x plus c. So what we do is we evaluate e to the x plus c at x equals 3 minus e to the x plus c evaluated at x equals to 1, okay? And so that turns out to be e to the 3, e cubed plus c, minus e plus c, which is, and then the c's will cancel for any c. Okay, and this is true, this holds true for any definite integral. All right, so the integration, and c of course is called the integration constant. It will always subtract off for a definite integral. So don't be overly consumed by that. Okay. Okay, so here's the evaluation operator. F of x evaluated from a to b. So yeah, so we've done this. Other common notations. I choose to use this notation right here for the evaluation bar. You know, the evaluation bar we've been talking about since day 1. All right. Find the area under the parabola y equals x squared from 0 to 1. Okay, so we go back to day 1 for this topic. So here it is. The area is equal, the definite integral from 0 to 1 of x squared dx. Take the antiderivative of x squared, which is x cubed over 3. evaluate it from 0 to 1. So that would be 1 cubed over 3 minus 0 cubed over 3, which is 1/3. So that's a lot less work than having to sum up the areas of a bunch of rectangles. Okay, so finally some efficiency. Okay. Yeah, much shorter method, no kidding. All right. So how about evaluating the definite integral from 3 to 6 of 1 over x? All right, so you know the antiderivative of 1 over x is the natural log of the absolute value of x. And so the function 1 over x is defined in the domain of integration. So f of x is equal to the natural log of x. So we can dispense with the absolute value. And so it's just ln 6 minus ln 3, which is ln 2. Okay, ln 6 minus ln 2. All right. Find the area under the cosine curve from 0 to b, where b is wedged between 0 and 2. So again, set up the integral. Okay, so the antiderivative of cosine x is sine x, so it'll be the sine b minus sine 0, which is sine b. And of course, b being pi halves, that would just be 1. So area is equal 1. Okay, so that validates that. Okay. Yeah, right, into 90. Okay. And there's talking about the travails of the ancients having difficulty with finding areas under curves. Okay, all right. Now, what's wrong with this calculation? Okay, so here's an interesting problem. The area under the curve of 1 over x squared from -1 to 3. And so if we blindly apply the fundamental theorem of calculus part 2, we take the antiderivative of x squared, which is negative of x to the -1, from 3 to -1, so that would be what? -1/3 minus 1, which is -4/3. Well, a couple of issues. First of all, 1 over x squared is always above the x-axis. And so how can you have a negative area if the curve is always above the x-axis? There's no area portion below the x-axis, so that should set off alarm bells right away. Because look at the sketch of 1 over x squared. It's like this. Okay? And we're integrating it from -1 to 3. So under no circumstances can this area ever be -4/3. Okay, so the problem with this is that this is actually, it does not exist, because the requirement is that the function must exist at every point on the interval of integration. And of course, 1 over x squared doesn't exist at x equals 0. It blows up at x equals 0. It goes off to infinity. And so you can't integrate around a vertical asymptote, right? So you'll have to wait until calculus 2 before you can actually find this area, give an estimate for this area. Okay. So that's the reason. 0 is in the interval of integration, and 0 is not in the domain of the function. Yeah, it violates the properties. Yeah, f of x equals 1 over x squared is not continuous on the interval of integration. It has an infinite discontinuity at x equals 0. So for now, we'll consider it as not existent. Perhaps forever. Okay. All right, so melding of the two parts of the FTC. Okay. So the derivative of the integral is the function itself. If f is integrated and then the result is differentiated, we get f back. So they're inverse processes. If we attempt to evaluate the definite integral of the derivative of the antiderivative, that turns out to be the antiderivative evaluated at b minus the antiderivative evaluated at a. And so f prime of x, of course, is equal to f of x. Take a function, differentiate it, and then integrate the result, we arrive back at the original function. Okay, so they're inverse processes. summary. Yep, the most important theorem of calculus, definitely no argument here. Yep, so now we can do the work of the ancient genius people without the fame. Okay, and all right, so this would be the conclusion of section 5.3. The fundamental theorem of calculus, one of the most profound theorems in mathematics that you will no doubt ever have to work with. Okay.